Okay guys, so the new content at the H2 is this microscopic idea of how current is formed. So the equation is I equals to NAVQ. If you just memorize it, you're going to not be able to use it because N is not a number. N actually refers to the number of carriers available per meter cube. So I use the word carriers, not charges, because sometimes the carriers have more than one charge. For example, in ionic compound, right, or ionic solution with 2+ valency ions, each carrier can carry 2 charges. Right? Like sulfates will carry 2 extra electrons, and your copper will carry 2 less electrons and become a charge carrier. So I equals to NADQ basically says that, hey, you know, if I have a conductor and a current flows through the conductor, right, this current must be due to the microscopic flow of charges. So that must be equal to depend on the speed at which they move through. Right? Because if they move faster, you should get a bigger current. If they move slower, you should get a smaller current. Because current is charged per unit time. Okay, it should also depend on the number of charges that one charge carrier carries. So for example, if for the same apples to apples comparison of number of charges, if I had sulfate ions versus chlorine ions, the sulfate ions should carry twice the current of the chlorine ions. But they have double the charge on each charge carrier. Okay, but most of the time I'm just going to stick to electrons here. So E will usually be E. Then A is the cross-sectional area and N is the number of carriers available per unit volume. Right? For example, if the number of carriers available per unit volume is the same for 2 substances, but one has a significantly bigger area, obviously there's more material inside for it to flow. So you should get a larger current. Right? So that's why I will depend on NA, V, and Q. Okay. So that's your H2 questions. Question 1, question 2, question 3, Ethan, question 3. Question 1, Afika, welcome back to the class. Afi, question 2, don't hear me. Okay, Afi, please draw a diagram to help me explain question 2. So I don't want just the working, I want you to be able to have working that helps explain.
Diagram. You want to draw like a pipe?
Yeah, like a pipe with stuff flowing through it.
Oh, let's copy from the notes.
I remember I used that in my lecture actually to help explain this thing.
How did it stick on?
I think so. Okay.
I put NAVQ. NAVQ. Small v capital A. Okay, let's put that done. I'll come up and explain. Okay. Yeah. Yes. Q is small q also. Avika is 17, right? Okay. Yes, correct.
This is the.
Avi,
Yeah, so I'm deciding which diagram you want to do. Wait, what
draw a
is
pipe to show the individual charge carriers.
Oh,
moving.
this one.
Yeah, it's the concept.
This one. The minus goes one way.
Oh.
Yeah. I think so.
Yeah, can you put away your phone? Thank you. Thank you. Put your table beside you. Okay, Ethan looking to divide by 2, right? They gave you the radius. Oh, the entire meter they gave you. Yeah, need to divide by 2. Yeah, okay. Where's my diagram, Abi?
Yeah, so I don't know. Is it just the pipe there?
Yeah, you need the pipe to show the two equivalent currents.
No, we draw like that situation.
You just draw the diagram of things moving hand already, right? Yeah, they can label the types. Yeah, we can start with minus. No matter lah. But it cannot be like that. I mean, all of the pluses are moving in one side, all the minuses are moving in the other side. Side. Okay, can. Africa first. How do you do your question? Correct. So you want the number of electrons flowing per second. That's rate of flow of electrons. They're not asking for the current, right? Okay then. So the total charge produced in the current flowing over time t is just the number of charge carriers times E. So this n is not the I equals to NABQ n, because it's just the number. Okay, this one you can use big N to represent, then you will be confused. Okay. So don't forget, in this question, your I must be SI units. So you convert the SI units because this will be in coulombs. Right? Sorry, Q will be in coulombs. So you need this one to be in SI units as well. So I will be in SI units 20 milliamps, and then what you will get should be C. Okay, good job, Africa. First question done. All you will do, right? Okay, question 2. Abi did this. Abi, the diagram, does it help me, man?
I didn't use the diagram, I just used the.
Yeah, lah, but must, right? Let's don't understand what's going on. So, never mind. Let's assume that the negative carriers, charge carriers are moving in one direction and the positive charge carriers are moving in the other. That's what the question seems to imply. Okay? Abi, when the positive charges move to the right, what's the direction of the current produced? Positive charge move to the right. What's the current produced? Why? So because conventional current is defined as the motion of positive charge carriers. Right? So this positive charge carrier moving to the right constitutes a conventional current moving to the right. But negative charge carriers moving to the left is equivalent to positive charge carriers moving to the right. So even though the negative charges are moving to the left, they constitute a conventional current going to the right. So actually what you should have here is that the current is actually the current due to the negative ions plus the current due to the positive ions. Right? And they're both in the same direction, that's why you can add them up together here nicely. Right? So what Abi has done is just take the number of charges that flow times electronic charge on each one. So this one is the number of negative ions times E plus the number of positive charges times E, then divided by the time. Right? That's how we calculated this. So I mean a little bit more working. Okay, your exam answers also should have a little bit more working like this to get your working mark. Yeah lah. And then you show that it's the sum of two currents lah. Right? Because the positive carriers give you their one current and the negative carriers give you a second current. You have to check whether they're in the same direction or not. For example, if all of the charge carriers were moving in one direction, the value will be less because the conventional currents will be in opposite direction. The equivalent current will be less. Right? Just the mass of one atom. Okay, so next one is done by Ethan. Okay, let me point out that he's wrong in one part. So this is the correct equation, but the number of charge carriers is not m over m. Because it's number of charge carriers per unit volume. So 8960 is not the mass, right? What's 8960? Yeah, this isn't density, right? This shouldn't be density. So this is wrong, right? So if I want to get the number of charge carriers, let's take a look. The number of, oh shit, I think Jolene can't see this. Let's move it a bit nearer. The number of charge carriers, N, is equal to the mass of the sample mass of the sample divided by the mass of one atom. If I do this ratio, I'll get the number of atoms. But it's not the number of atoms per unit volume. So I'll need to have 1 over volume here.
So let's say M.
That's not M.
Density A over.
Yeah, it's density over one atom's mass. So to show that, the mass of the sample is the density of the sample times the volume of the sample. Then this is the mass of one atom. Then 1 over V. That's why this is density over M1. So what Ethan should have right here is not mass of the sample over M1, but rather density of the sample over the mass of one atom. Then this will give you the number of charge carriers per unit volume. Okay, so actually this working needs to be inserted before you can write this step out. Okay, see how? Okay, we cannot anyhow just write the density divided by mass. We must have good reason one. Our physics everything can be derived. Man. Okay, Brendan, okay? Yeah. How do you do this? Yeah. You went here, okay. Right. Subsequently, his calculation is correct. So it doesn't anyhow whack or you really understand one. This one is anyhow whack or you understand.
Like the understanding is that just
Yeah.
how to do the thing.
But you cannot write M on top. I cannot skip steps for this. Okay. So you make V the subject. You get V equal to this. Let me just check whether it's correct or not. Should be C. Yep. Okay. This one is D, right? Okay. Okay, thanks guys. So of course, for Ethan to get the area, we need to use pi r squared. So you skip another step here, right? This one is pi r squared. And pi r squared is diameter divided by 2, and I use SI units. So don't forget to convert the millimeters to meters. Okay, so 8 millimeters divided by 2 will give you the radius. Then from the radius, then you can get pi r squared. Okay, I'll do question 4. So, question 4 basically is to tell us that, hey, this topic, right, in addition to understanding how the cells work, we should also understand that cells have an internal resistance, because when I construct a battery, there's inevitably some components that will produce a resistance when I use the battery. But there's an important distinction to make. The first thing to note, right, that I'm not talking about the question here, I'm just talking about internal resistance in general, is this. When I have any resistor, right, the PD across the resistance is 0 if there is no current flowing in it. Makes sense, right? Because current flows from high resistance to high potential to low potential. So even if I have a resistor in the circuit but there's no current, right, each resistor will have no PD. Make sense? However, a battery doesn't work that way. EMF of a battery is the potential to run a circuit current, a current through a circuit. So it is always there. That means even if I have a battery not connected to anything, there's a PV between these two ends because the EMF still exists in the battery. The battery is ready to convert chemical potential energy to electrical energy anytime, just that I haven't connected the circuit, but the E is there. So case in point is this. I can connect a voltmeter across the two ends of the battery. So the dotted line represents the entire battery itself, right? And we are saying that a battery, if it has internal resistance, can be thought of as a perfect EMF E with an internal resistance R that makes that it combined together in series. Right? So if I want to measure the terminal voltage, this terminal voltage, right, that I measure is equal to the EMF if there's no current. Because even though there's no current, the battery has an EMF. But the internal resistor will not have a PD because there is no current. Okay. However, if I open the circuit, then there will be a current going through the internal resistance. Then the terminal voltage of the battery will drop by whatever PD the internal resistance has. Because now I have the E minus away whatever this guy causes me to lose. So usually it will be less than the EMF E. Okay? Yeah. Okay, then we can get to this question proper. This question says that, hey, when I turn on the circuit, right, some energy is dissipated in the external resistance and some energy is dissipated in the internal resistance. Okay, so let's look at the external resistance. We can use our secondary school formula, P equals to I squared R, to say that, hey, the power developed in the battery, in the EMF, in the external resistance is just the work done over time. And that's going to be I squared R for the resistor. And 1,800 joules is used over 100 seconds. That produces a current going through the resistor times its resistance. So you should be able to get a current of something like 0.50 amperes. Square root 0.050. 0.50. Okay, all good. So now I know the current going through the circuit. Then I can apply conservation of energy. So the power developed by the cell is the amount of energy converted from chemical potential energy to electrical energy, right? By the cell for this period of time, for unit time. That energy is being used up by the internal resistance and the external resistance. But I know how much is being used because they told us. The external resistance uses 1800 joules and the internal resistance uses 200 joules. 200 joules, 1800 joules, and this took 100 seconds to happen. What formula can I use for the cell so that I can get EMF of the cell? Yeah, P equals to IV, right? But the V for the cell is E. So it's IV. Okay? And the I know. The I is just square root 0.50, which I found. Because everything is in series, so the same current goes through every circuit component. VI. So for a cell, it is E, because E is the PD of the cell. EMF. Okay? So this one you should be able to get the answer.
So is that 11 or across the field?
This one is whatever's on top.
Oh, okay.
Oh.
Okay, sorry. It's just this number here. Okay, I'm lazy to write out the whole fraction again. 28 point something, I think, the answer.
28.3.
It's not 11, it's all this number here. It's this thing here. Yeah. Yeah, this whole thing here. Okay? I just use the dot like on top thing. Okay, then you know you get something like 28.3 volts. So this one gives you answer. So two concepts to consider here right, is conservation of energy and V equals to IR. Keep applying and applying and applying again and again. But just be careful when you use equations, right? It must be power developed in R, in the current in R, which then R resistance of R. So all must be for that one object. Okay, don't anyhow use V's and I's and all that. Then that's where you'll make mistakes. Okay, let's discuss 5. So in 5 we have a simple circuit with switch, cell, and resistor. Okay, they say when the switch is closed, which one of these statements are correct? So let's investigate which of these statements are correct, which of these statements are wrong, and why they are wrong. Okay, so let's see. When S is closed, the PD across the battery can be measured with a voltmeter like this. False because the work done to move charges through the resistance R. Is that true? Alright. When I measure this PD, the terminal voltage, okay, I'm actually measuring the EMF of the cell minus away whatever PD is created by the internal resistance. Okay, so it's nothing to do with moving through the external resistance. But it is true that there is work done by moving charges through the external resistance, but it will not cause V to fall because the V falls not because of the external resistance. The V will apply over the external resistance, and that's EMF. So A is not correct. B, when the switch is closed, the PD across the battery falls because of work done by unit charge to move through the internal resistance. Yes. This is the reason, right? So, if I draw my diagram a bit better, basically if I connect this together, actually I have an internal resistance. So if I were to connect a voltmeter across it, okay, the voltmeter reading here will be the voltmeter reading will be EMF minus away IR. So this IR is due to the internal resistance. So B is the answer. Right, and we call this terminal PD. Okay, C is wrong as well. Because the EMF of the battery never ever falls. It is the terminal PD that falls, but the EMF itself remains constant. Because the EMF is the idealized EMF source. So C is wrong. And D, when the switch is closed, the EMF of the battery falls again, that's wrong. EMF doesn't change, right? The EMF of the battery doesn't change unless the battery is changed. Or the battery uses up its energy.
So terminal PD is only including the EMF nothing else, even the external sources.
Yeah, so the terminal PD doesn't depend on the external circuit. But it will actually, because the external circuit will change the current, and that will cause the PD drop because the internal resistance will change. So it does depend on the external circuit, but it doesn't drop because of the external circuit, it drops because of the internal resistance. Right? So basically, there's two parts of your battery, the ideal EMF and the internal resistance. The PD that the battery can supply to the external circuit is whatever EMF you have minus away whatever the internal resistance uses up. But the internal resistance will use up more if its current is higher. And the current will actually depend on the whole circuit resistance. Indirectly, yes. But the direct cause of why it drops is because of the internal resistance, not because of the external resistance. Okay, it's something to do with something inside the battery, not something outside the battery. How much it drops by, that one will be determined by something external. But the fact that it drops is not due to something external. C7 do A for me, thank you. Brother, you want to do B for me, thank you. Yeah.
Why when you do things in quantity, but when you test it on
Okay, now my brother will do question 7 later. Cool. Where are you going to do 6? It's the ratio that gives you the resistance.
yeah, like when the development takes this.
Not the other yet, because it's not the ratio. That's gradient.
But because R.
Yeah, that's not gradient. Gradient is BDR. So you might just keep taking division. Just calculate for 2 volt, 3 volt, 4 volt. Yes, 2 volt is 2 divided by 3, 3 volt is 3 divided by 3.7, and 4 volt is 4 divided by 4. Yeah. Okay, yeah, but show the value please. 4 over 4 will give you 1, but it's milliamps, so 1000. So for the 4 it will be 1000. So you just do coordinate of 4, 1000. Yeah, milliamps. So it's 1 volt over 1 milliamp. Like the right axis. Oh, basically you are supposed to calculate the resistance at each voltage.
Oh,
Like calculate by V over I. That's the resistance of the lamp. We are not asked to find the resistance of the lamp. You're asked to find the resistance of the voltmeter, right? A variable resistor, right? Yeah. So the graph is for the lamp. They're not done yet. You're almost done. This is resistance of lamp. So you still need to do some more calculation. So you look, everything else is in series, right? chairman.
Of what? Oh, chairman of what family?
That's a very difficult spot. I just find the fingers very painful. Yeah.
I'll throw the hands off.
This is hard.
JJ, share your this bad habit of writing numbers straight away after the variable. I want variable form first, then numbers. So you can show substitution.
See, I think for you, I think
Thank you.
Gonna go, you might as well try doing 7 now. It's just doing 7 now. What you rate 5 and 7? Yep, good job. That's it. Great. So you, then, instead of doing this, right, you could have, yeah, actually, whenever you get for 7, good job. I'm working with my rewrite this now. If you don't get comment, it's later. I'm not gonna say it's second order. No, I think it's not 1 over A relationship, right? It should be quadratic. Yeah. So, when you say it's proportional to what L, when it's proportional to 1 over A, when you stretch, right? L will increase and A will increase. No, when you stretch, L will increase, A will decrease, so 1 over A will increase. But how does the increase happen? Is it the same ratio of increase? It's not. So you're going to need to express L and A as a function of B. Later the function of B. So, question 7 a bit difficult. Please do take a look again. It's not that easy. Yeah, please go try to figure it out. Question 7 is not easy.
Still like too thin, you see.
Hey, yeah, better go use the other one, please.
I'll see.
I do like.
I can zoom in and everything.
No, yeah. Okay. So all this is technically not correct, right? What's the x-axis? So you want to express A in terms of B and L. Okay, let's take a look at the work that has been done. JJ did question 6, so JJ, you explain yourself.
You read the resistance of the graph.
Yeah, they want the resistance of the variable resistor, not the lamp, right?
So after you read the current of the graph, then you just use R equal to V over I.
But I don't know VR.
The V of
This graph is what?
this is for the left.
This is the lamp, right?
Yeah.
So at this current, the lamp is actually 1.4 volts. But I don't know this one. Right? What's the potential difference across the variable resistor?
You take the total E minus.
Take the total E minus the lamp's potential difference, which you read out to be 1.4. Then you actually get the potential difference across the variable resistor. Okay, then you use V equals to IR to get 1040. Then you get this one. You guys got it? See how to get 1040? Okay, so this part's doable, right? So JJ made careless mistake. He didn't see the question asking for the lamp, or he thought that the graph was for the variable resistor. Okay, here second part.
Yes.
Tell us what you have learned. What are we trying to draw here?
We're trying to draw ask the resistance against voltage.
Yeah.
So then I just calculated the resistance using the values from the graph. So at 1, at V equals to 1, then I put the value of I at that value of V, and then using the equation R equals to V over I found the value of R.
Yeah. So you must use V over I. You cannot use gradient of the graph. It must always be ratio. That means division. So you must take V1 divided by the current to get this value. Okay, don't forget the current is given in milliamps, so convert to amps. So the 4 values you should get is like that, and then you should end up with some kind of curve. Okay? Yep.
So must we use the 4 coordinates for 1, 2, 3, 4?
Yes.
Oh.
That's why there's 4 marks in this question. They want you to use coordinate to calculate to draw the graph, because the graph is not linear. Okay, so since you use those points to calculate, please go label on the graph as well that they are calculated.
Wait, so all the values need to be written out.
Yeah.
On the graph, yes.
This was my graph. I wrote 2.
Yeah, but then 2 points won't give you a curve, right?
But like you use filament and logic, but they will go faster.
Yeah, but how does it go up? Does it go up like this? Or does it go up like this? Or does it go up like this? You need to be able to differentiate this. And the only way is to just take 4 plots and try. Right? So that's why this question you need to plot. You need to go calculate the resistance. Now, resistance is not equal to dV dI. So you can't look at the VI graph or the IV graph and find the gradient. It doesn't work. Resistance is ratio. Okay, I think I harped on this a lot in the lecture. It must be V divided by I. It cannot be gradient. Okay? Okay, let me just quickly repeat Ethan's working because I think that part is out of the camera. So, resistance of a wire or any conductor is rho L over A. So, Ethan, you want to guide me through how to derive this?
Sure.
Hey, sorry, Brandon, you want to guide me through how to do this?
First,
The question says?
the question gives 2 axes. The one that is the y-axis and the other is the x-axis.
Okay, so I'm supposed to plot the R versus
The x, the
length graph. Okay, can?
need to make R the subject. You have to express R in terms of L.
Correct. So I have to express R in terms of L, but there's A and A changes in this question. So the question says volume equal to constant, but the wire is being stretched. So L and A both change, right? So I need to get rid of A. How to get rid of A?
Volume equals to length times area.
Volume equals to L times cross-sectional area.
Then you make A the subject.
Make A a subject. Volume over length. Then sub back into my equation.
Yeah.
So there's only one variable, this is a constant, this is a constant. So it's proportional to L squared. So we should get a quadratic graph. Okay, the closest to a quadratic graph is C. Okay. Okay, let's take a look at 8 and 9. Okay, question 8, right? They tell us that there's a current going through a slice of material. And then they give us the dimensions of the material, right? In the dimensions of the material here given, L is 1.8 times 10 to the power minus 2. And A, the cross-sectional area, is 1.2 times 10 to the power minus 3. What width times the height. Right? So this is actually the L and the A in this question. So actually the L and the A depends on which direction the current flows through the block. So if my block is like this, right? And my current flows this way, this resistance would be different from if the current flew this way out. Right? And then this is I2. And the resistance will also be different compared to a current that flows from the top down through this material, because the L's and the A's are different for each case, even though the block is the same. Right? So it depends on the orientation in which the current is made to flow. So R equals to rho L over A. And the question says the slice dissipates 400 milliwatts of heat energy. Okay, so power is I square R. If I want to get rho, I can just simply say I square RA over L. So in this case, the current is 40 milliamps. 40 milliamps square. The length is here, 1.8 times 10 to the power minus 2. The area is here. And I need R, the resistance. So, oh shit, the resistance is not given. Yeah, correct. So I'm going to need to use it to find the resistance. So P equals to I square R. The resistance is just P over I square. 250. Okay, so it's 40 milliamps. And the power is 400 milliwatts. 250, huh? You know, it should be a nice number. Oh, because we're 4 square. So 1 quarter equal, okay, 250 ohms, is it? Okay, then we can put it in times 250 ohms. So you should be able to get a formula, a value for resistivity. Should have gotten something like 0.25 ohm meter. Okay, and this one is in. Do you manage to get this one?
So CJD, this is quite symbolic form of way to like give you more chance of getting a
So how do you do this one? You write a symbolic form for your working to expand it. Okay, but this is the step here. Power equal 400 milliwatt over I square over power. Right now, let's see my working next time. How can I check that you are prepared for the exam? I'm not. Okay, well. How do you get D though? Okay, question 9 is our challenging question. So let's think about it together. Okay, question 9. We got a wire. And let's say this wire is length L. Then I chop it up into n parts. Right? And then I take the n parts, right, and combine them together to get a bundled wire whose resistance is R. Okay, they want the resistance of the original wire. So first you're going to look at the bundled wire. How are they arranged like this when it's bundled together? Now imagine if I wanted to find the connect to let a current flow through this resistor, right? All I need to do is take this and connect it to a battery, right? So how are these wires connected?
They are insulated.
Yeah, doesn't matter. Actually, it doesn't matter.
Oh, in parallel.
Yeah, they're like in parallel. So actually, it doesn't matter that they're insulated or not. Even if they're not insulated, it's as if they are insulated. Because the current will just keep flowing through them in the length direction. There's no reason for the current to flow between strands because there's no potential difference between the strand at each point. The potential difference is between the left and the right side from the battery. Right? So it doesn't matter that they don't need to be insulated within the bundle. Okay? All good? Yep. So, these guys are in parallel. Okay, let's write a few things. Let's call the resistance of the original wire R naught. Okay? So, if the original resistance of the wire is R naught, and I cut it into n parts, then the resistance of one part is resistance of one strand. We can calculate it. Okay? It is just R naught divided by the n number of resistors that I have. Okay? Then, when I join that in parallel, right? Many strands are put together in parallel. Then, I would say that the resistance of the cable is R. But R is just 1 over R1 plus 1 over R2 plus dot 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 plus 1 over Rn to the inverse, because this is the parallel resistors formula. Right? Each of them have resistance R1, R2, R3, R4, so on and so forth. So this one, right, because it's R naught over N, the inverse, I cannot just inverse, right? I need to inverse this first. So it's actually N over R naught. N over R naught plus N over R naught plus dot 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 N over R naught. Inverse. Right? Because this is 1 over R1. R1 is R naught over N. So the inverse of it is N over R naught. So I add up N, the denominators are all the same, which means I add up N times. Right? So this one becomes N times 2 to the power of 2 because it's N times of N, so it's N squared. Right? Then over R naught and then inverse. So when I inverse this, I end up with R naught over N squared. So if I want to find the original resistance of the wire, R naught, it is just N squared times R. So you get N squared. So this one should be D. It's a bit complicated, but you see if you do diagram right and label values, not label values, but create variables to solve it, right? Actually it's a lot easier.
I use like R equals to the PL over the part. I got it.
So what do you do?
Like I mean like let R equals to resistivity over it. Then the R then equals to so
Basically, what you do is you assume that this one has some cross-sectional area small a, right? and you assume that this is a bundle of cross-sectional bit A, and of course this bundle A is A times N, this cross-sectional area A is just a small cross-sectional area times N of them. So JJ, remember you said insulated, actually it doesn't need to be insulated. What they have imagined, right, is my individual strands, right, combined to be one thick cable of bigger diameter. So of course technically there's a bit of error here. The error is that the cross-sectional area is, there's no error here, but in practical case, of course there is spaces between them. So it's not the true cross-sectional area of the new cable, but the total sum of areas of the individual cables. So that you're using resistivity to create a thick cable from individual strands. You will work out to get the same answer. Okay, so if you're not sure, why don't I challenge you to try this alternative formula, which means you need to consider what the resistivity of the material is here. It will be the same resistivity here, it's just that your L will now change. Right? The L will now be shorter because you have less strands. You will end up with the same result. See how I try? Let me consider resistivity and make a thick bundle from the new bundle. The thick cable from the new bundle. Which method do you do to get answer? Mine or Richard? You told me this, is it?
No, it's something like that.
Yes, the idea is the same. Which method do you do? Or you do the solve this one? Okay, for your answer, the way that I did it, basically I consider it being parallel, right? But it's identical as you assume that all the strands become one thicker wire because of another area. We're going to try the other method. See what whether you can get n squared r as well. So actually this question, right, shows you why your resistance will decrease when you have a thicker cable, right? Because it's as if you have many thin cables in parallel together, and when you connect resistors in parallel, the overall resistance will drop, right? You know that when you connect two resistors in parallel, the resistance will fall, right? The effective resistance will fall. So when you have a thick cable, it's as if you have two half thin cables joined together, or four even thinner cables joined together. So thin cables have high resistance, but thick cables have low resistance because it's like having many in parallel like that. Okay? How we look at it microscopically is, hey, you know, if I have a terminal here and here, and this terminal is 5 volts, this terminal is 0 volts because I connect it to some kind of 5 volt battery. Okay? Then the potential difference is between the two ends. So it's possible for me to have, say, two wires here that are not insulated, but the current won't flow vertically between them. They will always flow horizontally because the potential difference is from left to right as applied by the external voltage. Right? And there's no potential difference between top and bottom. So let's say, for example, in the middle, right? Here is 2.5 volts. But it is 2.5 volts on top and 2.5 volts below. So there's no reason for the current to flow in the vertical direction at all. There's no Y component flowing of current. JJ, just now you talked about the insulation, right? So this is why we don't need insulation. Because at any point, the potential on top and below is the same. And inside as well. So there's no reason for current to suddenly dive down and go back up again. So they don't need to be insulated within the cable. Okay, so if a multi-strand wire, this will work. Which is also why if you want, say, to support a higher current, the wires you get are thicker. But if you unravel inside, right, actually there are multiple wires stuck together in the braid to make it stronger. The braid is actually stronger than having a thick cable. Okay. Alright, I think this is a good place to stop. Next tutorial we will do question 10 and 11, which means we will need to prepare some DC circuit, electric field questions already. Okay. Sorry, Brandon, what's up? Because the current questions are not that difficult, right? I think so. I mean the what questions are a lot more difficult, the DC circuit questions.